Awesome. You can start now, Aarav.
Yeah. Hello. So today's class will be on. So can anyone tell me counting means? Oh, I'm audible.
Yes, you are audible. I think you just asked the in more P6 level question, right?
Okay, fine. I'll just tell it myself. So it this is basically a process where you're counting the number of uh, elements in some set. So for example, you have this notation and choose R. Basically, what this is defined as is the number of subsets of uh, 1 till n that have size R. So this is defined as n factorial upon R factorial into n minus R factorial. Does anyone have in would anyone like to share a way to prove this?
I mean, there was one way, I guess. Yeah. So, acha, you're asking the proof of NCR?
Yeah.
No, I don't have. I am. That's my question. How is NCR this?
Hmm. Okay. So
Count the number of permutations and then divide by how a specific thing can be counted.
Yeah, but you are like NPR divided by R factorial, but you don't know what how to prove NPR. So it's like circular logic you're getting that.
but you can prove NPR too.
Yeah, it can be.
Like if you provide a proof of both, then obviously it'd be done. Okay. So
We have
let's.
to prove the fundamental principle of counting. Then we can prove easily.
I mean, it's all right. You can like take that for granted.
So there can be one way. Like first of all, we can first prove what is a permutation. Like if we choose our first, like there are permutations. Like
Yes.
we can add the set in any way. So the first we can choose first r numbers of the set, and there the first r numbers can be permitted in r factorial ways, and the r n minus r objects left can also be permitted in n minus r factorial ways. So we can prove it by that thing. So they
Hmm.
must be divided in our.
Yes, that is correct. Although I realize I should probably define uh, n factorial. So n factorial is just the permutations of uh, 1 to n, and this is basically product of 1, 2, 3 up to n. That is because in the permutation you can choose the first element in n and the second element in n minus 1 way since 1 is already chosen and so on. So for this basically now there are two ways. One is the thing which you said. So you take 1 to n, you permute them in n factorial ways, and then you choose the first star. So now you count how many times each particular subset which size R is being chosen. So let the set is A1 till AR, which is S. So let's just call this for the time being box. Yeah. So you have you need the first R elements of the permutation to be S in some order, and then the next n minus R to be box n minus S. So for that, if you have like this subset of size R, then the number of permutations where the first R elements are these will be R factorial into n minus R factorial. Since these R elements can be in any order in the first R elements, and then the next n minus R elements can be in any order. Does everyone get this, or should I repeat something?
Yeah, got it.
Okay, I'll do it once more. Like, you told that for permutations of S, there will be n factorial. And how did you get the denominator?
Denominator, this is where is there in denominator?
No, like here you have to okay. So for like what you told, I guess was for the set S, you have to do n factorial, and if you're choosing any R objects, so for permuting
Oh
them,
no, I did not like talk about n factorial. Like just forget this result for me. I'm saying like this is there like any thing which you did not understand. I like get to this very soon.
Okay.
You understood this, right? Okay. So now if like let us say there are k sets. Okay, there are actually n choose R sets. So there's just n choose R. So this is the number of like number of subsets of size R multiplied by the number of permutations that each subset of size R appears in. Is the way for which the first R this set S. This should be equal to the total number of permutation, because every permutation will have some set of first R digits. This should be n factorial, which will complete. Is this clear?
Yeah, okay.
No, I don't understand.
What part of this don't you understand?
What does this and choose as a subset of n factorial mean? I wasn't able to understand this part.
Okay,
This
so
entire thing being subset of n factorial.
like n factorial like is a number. It won't have any subset. But what I did is like this is the number of subsets of size R, and each subset of size R appears in these many permutations. So this project is
Okay.
the total number of permutations.
Okay.
Okay. So the second method is recurrence.
Can you say what is recurrence?
Yeah, okay. I mean, it is basically where you like basically it is induction on R. You have n is greater than or equal to R in this, because I should have defined it earlier, but it's just assume this for now. So in recurrence, basically
Right.
you prove this result for R is equal to 0, R is equal to 1, and then prove that if it is true for R is equal to I, then it is true for R is equal to I plus 1, which is basically induction. But like technically in this we will do strong induction or weak induction, but yes, you get the point.
We should first prove that this is true for one, and then
Yes. So for n is equal to 0, this sorry, R
the recurrence proof is just induction.
yes.
My
So
question is the recurrence proof is just induction.
yeah, recurrence proof is just induction. Like recurrence is basically induction only. So for R is equal to 0, this n choose R will become n factorial upon 0 factorial, which is 1, into n minus 0 factorial. Oh yeah, should have also said 0 factorial is 1, because it is not very clear with this notation. So and then for r is equal to 0, this will become 1. For r is equal to 1, this will become n factorial. On 1 factorial, which is 1 times n minus 1 factorial. But n factorial will be n into n minus 1 factorial. So for n choose 1, this is also n. See, you have wait, actually, yeah, sorry. I think I'm like inducting on n would be a better idea. Yes, I'm meant induction on n only. My bad. I did induction on r. So you have 1 choose 0 is equal to 1 by this logic only, and which is also equal to 1 choose 1, and n choose 0 is you can take it as 1. Then you want to prove that n choose r is equal to n minus 1 choose r plus n minus 1 choose r minus 1. And after this, you can just like do algebra, which I will leave up to you. But does anyone have a way that we can prove this? Like, don't use this formula, just use the definition of n choose r. Can anyone prove this using that?
We can take out a leading element. Let's say we take out a from the subset. Now there are only two situations. Either a is in the subset of r, either a is in the subset or a is not in the subset. So both the conditions, considering both the conditions, we get to this state.
Yeah, exactly. That is the proof. So you have 1 till n is the set. So n choose r is the number of r element subsets that either contain 1. So if it contains 1, out of these n minus 1, it contains r minus 1. So you have n minus 1 choose r minus 1 is a subset which contain 1 and r element. But then if they don't contain 1 and of these n minus 1, they contain r. So n minus 1 choose r is the ones that contain which don't contain. So these are the ones that contain 1, these are the ones that don't contain 1. So when you add them together, they contain sorry, yeah, they are the total number of r element subsets of
Also,
1.
can't we somehow use combinatorial argument? Like this is how our LHS is how we choose choose R objects from N objects. and,
This
and
is combinatorial.
yeah.
This is combinatorial only, right?
Oh.
And then, like, if you wanted to say something, then you can.
No. I was not. I was there. It's like if you were using the choose thing, like there are N objects you can do like.
Okay, cool. So from like this point on, can everyone proceed with algebra? I leave it as an exercise.
Yeah.
Okay, so now prove this.
This, I guess, we have two methods. Actually, I have read two.
Go ahead.
First, we can use induction,
Hmm.
or we can actually show bijection of two sets. One is this, and The second is of binary numbers. That too.
Right. So I'll just give the induction, sorry, the bijective solution. So by bijection, what I mean is that to show two quantities are equal, you take a set with size of the first element, another set with size of the second element, and then you establish a bijective function between the one, I, which is both injective and surjective. So, well, in this case, what we'll do, prove is that the number of elements of the number of subsets of is this, but it is also this. So the motivation for this is n choose r is basically the number of r element subsets of 1 to n. So if you sum from 0 to n, you get the subsets of any size 1 to n. So it is reasonable to assume that see that this is number of subsets of n. But then how do you prove that this is the number of subsets of?
We can create a binary string of length n.
Uh,
I
binary
mean,
string.
any element in N has two options, whether to be in that set or whether to not be in that set. So it each will have two, so two to the other, the number of options.
Yes, that is correct. So basically, what you do is you we can do induction as well. So you count the number of sets that n is, where if it is either in the set, then now the remaining n minus one, let's say by induction you have to choose, you have to the power of n minus one subsets and then you add an n, or you can just have to the power of n minus one subsets without adding n, which would add to the power of n. The induction hypothesis is just the number of subsets of one, which is just two, the null set and only one. So, or we can phrase this in another way that for every element I is either in a subset or not in a subset. There are two options of each element being in the set or not in the set. So multiplying this over all the elements, you get to the power of n possible subsets. So, is everyone clear with this?
This is by the principle of fundamental counting.
Yes.
Yeah. And we coin method that how many coins head and tail this.
Coin method? Uh, like, could you elaborate? Not aware of any coin method.
Is he talking about the stars and bars method? Yes. Weather one.
You can use that for this one.
No, no, no. I just say this is
Yes, wait, go on. Okay, okay, but also someone was talking about some binary string idea to prove the number of subsets to the power of n. Could they elaborate on that, please, if they want to?
Yeah, so I was saying that we can create a binary string of length n, in which we can write 0 if the particular element is not in the subset, and we can write 1 if particular element is in the subset. Then we have two choices for each of the elements, so applying the multiplication rule, we get 2 raised power n.
Okay, so that is the same thing that we did here, but I suppose that is a nice way to phrase it. So thank you. Now, prove that for any integer k. I'll just use some notation from now on. Prove that for any positive integer k. Everyone understands some notation, right? Which set? Yes. So could anyone prove this? The k is equal to 1 case you did here.
Wait, you're telling us to prove the reverse of the binomial theorem?
I'm proving it. I'm asking you to prove the binomial theorem, but for integers, positive integers.
Is k be any positive integer?
Oh yes. Okay, I'll give you guys 2 minutes to try to prove.
Yeah, it is also the same case. Can I go on?
Oh, sure. If you think you have a proof. I mean, you have a proof.
Like we can expand the right hand side and then we can compare coefficients. Like we can see that how many times we have k raised per n. So how many choices do we have from the n to make k raised per n? And we see that there are n out of n choices because there are only n items in the right hand side. So similarly we can do the same thing with other terms.
Well, yes, good. Your solution is correct, but like I mentioned, k is belongs to z plus because I wanted the combinatorial proof. Although yes, you proved generalized binomial theorem, which is, I mean, for complex numbers as well.
By the way, isn't there just induction on K? Like K equal 1 works, so we can do strong induction, like 1 to K works and K plus 1 we will just consider.
Uh, you're saying you prove this for k is equal to 1, which you
Yeah,
already did an induction k.
yeah, we do this for K plus 1, it works. So we just
Yes,
try
okay,
to
that is, you're on the right track. That is the solution that I had in mind. Could you elaborate on how you are intending on doing?
okay, like okay, um, like K plus something works. Oh yeah, yeah. Like so we have the sum of all those. So if we replace k with k plus 1 and just try to find the sum, we already have Yeah, we like no, one second. It's like k we have k satisfies, so we need to prove this happens for k plus 2. Okay. No, right. Yeah. So, if we put suppose we set up the induction hypothesis, then we suppose see that k equals k works. Then we try to prove for k plus one. Now, as k works, so we have the expansion for k plus one. Now, when we put k plus one in place of k, we have the expansion of k plus one. We substitute it with this, and we find that the LHS will be equal to RH. If you understand what I'm saying.
Hmm. Okay, I think that is correct, but you will have this, but that, okay, well, I mean, yes, I think that probably works because then you will, for the coefficient of k3 power of j, and so like
No, no.
you're saying for k plus
Wait.
1,
Yeah.
uh,
So. Yeah, we get n here. Can you see?
yes,
Yeah. So here, as we are inducting, we just put it as k plus 1 to the j, right? Now, as
yes,
k plus 1 to the j. Now, as we know that case this satisfies, so we already have the expansion of this. So we just replace the expansion here, and we have to prove this is equal to k plus 2j, and we can just compare it like that. That's what I'm saying.
uh, k plus to the power of n, you mean?
Yeah, yeah, and sorry.
But then how will you compute k plus to the power of n?
Like we have to or we have to factor it, I guess. I'm not sure. This was my idea, though. Not sure.
Will it be beneficial if we induct on n?
Yeah, you can probably induct on n, but hmm. Okay, so I'll just say what I had in mind then. So you prove by induction on k that k to the power of I is the number of uh, sets of k subsets that sorry, k plus 1 to the power of I. So, okay, let's just say k to the power of I is the number of set of subsets a1, which is a subset of a2, and so on till a sub k minus 1, which are all subsets of 1 to I. So does anyone have any ideas on how to do this? How to prove this? The
How did
result is clear, right? What I'm trying to conjecture.
can you repeat this line like you just wrote it?
So I'm saying k to the power of I is the number of set of k minus 1 subsets a1, which is a subset of a2, which is a subset of a3, and so on until a sub k minus k is a subset of a sub k minus 1, and all of them are subsets of I. So can you prove that the number of such set of k minus 1 subsets is k to the power of I?
What is the subset AI here? Couldn't really get it.
AI is just like a subset that we define. We want to count the number of such subsets. Like in this, we are just counting A1 belongs to uh, sorry, A1 is a subset of N.
No, I still couldn't get it really. But how did you define this?
What part don't you get? You don't get what A1 means.
Yeah, and how this series came.
Like you're just this series, like it did not come from anywhere. You're defining this series. Got it now?
Can maybe explain the series once again, just what it is, maybe.
Okay, I'll just give an example then. Like, for example, you want to prove that 3 to the power of 3 with, no, okay, let's say 3 to the power of 2 is the number of subsets E1 belongs to E2, a subset of E2, or which is a subset of with. So you want to prove that there are 9 such sets, which are this can be fine. This case, this can be any of the 4 subsets that of 1 or 2. It's like 5, 1, 2, and 1, 2. So this has 4 possible choices. This can be 1, but then this must be having 1, and it also must be a subset of 1, 2. So it can be either 1 or 1, 2. So there are 2 possible choices. Similarly, if this is 2, there are 2 possible choices. And if this is, then this must contain both 1 and 2, but it also cannot contain any other element. So there is one possible case. So this comes out to be 9, which is 3 square. So you want to prove the generalized statement with 3 replace with k and 2 replace with 5. Now, is it clear?
Yeah.
Okay. Okay, I'll give another. Okay, wait. So yeah, I was proving this. So how you prove this is that for every element of box, let's say J, it can be in none of these. It can also be in only A. It can, wait, sorry, no, only AK minus 1. It can be an AK minus 1 and AK minus 2. It can be in either 0 of none of these, one of these, two of these, and so on until k of these. And if it is in some particular number of these, it must be the last few. Like if say it is in 7 of them, it must be in the last 7 subsets in this series. So J can be in any number from 0 to k minus 1 subsets. So for any J, you can just assign a value between these two and you will be done. So the total number of such, uh, like, so you just assign a number between 0 and k minus 1 I times. So is this clear now? Okay, I'll explain again. So basically what I'm saying is that every element of this set, you can have it in none of these A's. You can have it in only AK minus 1. You can have it in only AK minus 2 and AK minus 1. And so on. But it must be in like some consecutive block at the end of this series. So for each element J in the set, it can be in any number between 0 and k minus 1 such subsets, and fixing such a value for all j will uniquely define this set. So you have k to the power of I possibilities. Okay, is this understood? Oh, hello.
Yeah.
Hmm. Okay, so now what is n choose I into k to the power of I? So in n choose I, you choose some set. Let let's just call it a sub k. You will get why I'm calling it a sub k, not a sub 1 or something when I'm done with the done with my argument. So this is some counting the number of sets A sub k, which belongs to box N, and then this is set I, and then K sub I just follows this up with K minus 1 further subsets. This is understood. Okay, I'm gonna take that as a yes. So you, so basically this is finding this value, but you replace K minus 1 with K, and then you add an additional condition that A sub K must have size I. So yes, now we're done. But now you're summing over all I from 0 to n. This can be any subset. So you're actually finding all such chains of K consecutive subsets that are a subset of the succeeding one. So, but we already proved this. This is actually just K plus 1 to the power of n. So we are done. So everyone got that. Okay, so now I will just share 3 problems which you guys can do. Okay, so I'll give like some time to for you guys to work on these problems.
Can you explain the first problem once?
Okay, so for any finite set S, let modest the number of elements in it. So basically, you want to find uh, like this pair, this like ordered pair of subsets. Order means that if you say find 1, comma 2, and then you find 2, comma 1, these two will be considered as different. And you basically need to find these. So the number of elements in A multiplied by the number of elements in B is equal to the number of elements present in B multiplied by the number of elements present in their union.
Okay.
The second question is not visible.
Which
Yeah, now
question?
fine.
Also, like when you chat, it doesn't get included in the recording. So, yeah, like if you have any approach that you think might work or anything, feel free to unmute and have a discussion about it till then.
Yes.
Could you please zoom in a bit more? I can see the second. Yeah, thanks.
Now fine, right?
By the way, like if both of the subsets A and B are phi, then A intersection B is also phi, right? And A union B is also
Yes, yes. 5, 5 words.
okay. So it should be zero. It's phi is zero, right?
Well, phi is not zero. Like phi is a set.
Means
Zero.
cardinality of the
Yes,
subset
yes.
phi is zero.
Yeah.
Can we somehow try and make cases and then eliminate one by one for the first question?
What do you mean by wait? Like, you mean making cases on what A and B can be? That would be. I mean, you can do that, but
So we can make cases for the left hand side. There are total
oh, you mean like make
cases.
a case on what uh, cardinalities of A and B are?
Yeah.
Yes, I think you could do that.
I think making cases for A intersection B works better because A intersection B cases, if you get some cases, it will be like very bounding. Like for example, if you get A intersection B equals 1, you only get one element that is common between A and B. So that bounds it very well.
Okay,
Right.
well, you could do that, but I'd suggest you not to do that. That would be a very time-taking process. As a Okay, should I like reveal a hint?
Just let me try it and I will.
Okay.
Is that property useful that A intersection B is A plus B minus A union B?
Sorry, I didn't quite catch that. Could you repeat?
I said that if the property A intersection B is equals to A union B minus A plus B minus A union B helpful.
Oh, well, yes, you are on the right track.
Okay, can you give a hint?
Okay, hint is basically what he said. Uh, okay, this is the hint for the proof of this. You can just
Hello?
okay, so for the proof of this, if you can do, uh, you can take any element I belonging to A union B with, I mean, I belonging to A or B. That is, uh, we can just say that by saying A union B. So you can take some I belonging to A union B, make case on whether it appears in A, B, or both, and in either case you can compare the number of times it is included in this sum and included in this. Like for example, if it only appears in A, then over here it will be counted once. Over here it will be not counted. Over here also it will not be in the set, so it will not be counted in this cardinality. When this it will be. Similarly, if it is in both, it will be counted here and here, but it will also be counted here and here. So you have 1 plus 1 is equal to 1 plus 1, which is
We can
obvious.
prove it using Venn diagrams as well, no?
Yes, you can. So for that, you basically take this set A and B. This is basically like the space containing all the set elements of set A. This contains all the elements of set B. This is A union B, sorry, A intersection B, and this is A union B. So there, some you are counting basically everything once, but this region twice. And if we take A plus B, then you are counting everything once again, but this region twice. So yes, you will end up with the same sum.
Hello.
Hello.
Yeah. So for the last sum number 3,
Yes.
I think I have solution. So essentially, if we are to do if we are to solve this, essentially we have to partition the numbers 1 to 13 into two sequences essentially. So say sequence A and sequence B, where sequence A has I elements and sequence B has J elements. And sequence A should have A1 less than A2 less than AI. And for sequence,
Sorry, could you repeat the last part? I didn't catch that.
so essentially for the last sum, you have to partition the 13 cards into two sequences.
Right.
Where for say the sequences are A and B. So for both sequences A and B, AI needs to be less than AJ for all I less than J, and BI needs to be less than BJ for all I less than J. So
Yes.
the number of
Basically, what we're
ways,
saying is we want to partition this into 1, 2 till k, and then k plus 1 to 30. That's what you want to do, right?
yes,
Yes. Okay. That is a good way to start.
and then we'll have to find how to interleave these to get a solution.
Yes.
Can we use systematic counting in problem number 2?
Systematic counting, like what
Yeah,
making cases.
I have a very problem too. Like, yeah, one thing is like anything after 7 cannot be paired with a greater number, right? Because there is no number that's like 2 times 8 or 9 or 10. So anything after
Yes.
7 will be paired with a lesser number. And 7 has two options. One, it can be paired with 14, or one, it can be paired with 3 or 2 or 1. So this how we can make cases and do, I guess, for problem 2.
Yes. Okay. You are on the right path.
And also one more thing, for the problem one, once you gave us the hint that that cardinality of A plus cardinality of B equals cardinality of A intersection B and this one, and we have the same number. So what if we replace cardinality of A as X, cardinality of B as Y, and A union B as A and A intersection B as B? Then we get X into Y equals A into B, and X plus Y equals A plus B, where all are integers. So we have a different, we have two different things, I guess. Like if we do.
Well, yes. That is kind of how you do that.
Okay.
Is the answer for the problem number 2 is 49?
2. Wait. I don't think it is 49.
Can we somehow use graph theory? I don't know why it's so intuitive to use graph theory in problem 2.
Well, you are welcome to try. I suppose it could be phrased in a graph theoretic way, but I'm not aware of anything of that sort.
Like, is the answer for the second problem 12 by any chance? Like, I may be making a mistake, but what's the answer?
Answer is 12. What?
Is it the second problem? Is the answer 12?
12. Wait, let me check. No, the answer is not 12.
One thing which I did observe was that suppose I start with 7. For example, I'm telling that 7 goes to a smaller number. 7 is paired up with a smaller number for the second problem. If I tell that, for example, 7 is paired up with 3, right? For example. Okay, so now what I'm getting is that 8 can be paired up with 4, 3, 2, 1. Now for like I'm telling you 8 is paired up with 4, then 9 will have strict options. So like this we have after each we are getting strict options. Like for example, the highest numbers change, the highest number which can be paired changes after every two. Like for example, highest number which we can pair 8 and 9 which is 4, highest number which we can pair 10 and 11 is 5 and so on. So highest number changes every twice. So if we even if we pair the highest number with another number, the next number will always remain empty, and we have to pair it with a lower number. And as the highest number before that is already paired up, so we have to pair it with even lower numbers. So this is how we can form an induction, I guess.
So like what you're trying to say is that 7 is you want to prove that 7 is connected to the number which is greater than 7.
No, 7 is connected with a number that's greater than no. If 7 is connected with a number greater than it, it can only be connected with 14. So we are
And
leaving that case.
that is true, since 7 is, if 7 is like connected with a number greater than it, then the greater number is not 7. 7 is a smaller number. The greater number is at least 2 times 7, which is
Yeah.
14.
Yeah. So that's why I was telling that if 7 is connected with a greater number, it can only be connected with 14. But if it is connected with a lesser number, the 7 can be connected with 3 or 2 or 1.
Yes.
Right. Yeah. So now what I'm telling is that if we so suppose I'm connecting 7 with a smaller number, for example 3, then we will have for 8 we will have options 4, 2, 1. Suppose we connect it with 4, then for 9 we'll have only 2 and 1. So, like what I'm saying is that we can provide an induction that like if a number is connected with the highest number possible, and the number next to it also is connected with the highest number possible, then the number after that will only have very less options. So that's how we can form an induction, I guess.
If a number is connected to
Wait, can I write?
okay.
Yeah. So what I was telling is that yeah. So 7. What I was saying is that 7 is connected with 3, for instance.
Yeah.
And
Okay.
yeah, so then we for 8 we will have how many options? We will have 4, 3, 2, 1, 4, comma 3, comma 2, comma 1. But so as 7 is connected with 3, we don't have this option. So suppose I connect with this. But for 9, we again have 4, 3, 2, 1, right? But all of them are rejected. So we will only have to suppose we connect it with this. So for 10, what we then this is an interesting thing. 5, 2, 1, 5 and 1, because 9 is connected. Then let's do 10 with 5. But for 11, it's 11 we have to do 1. But for 12, it's 6 only. 6 is the only possible thing. But for
And
13,
you are logged.
yeah. So what I was saying is that for 13 we have no possible solutions. You're
Well,
getting
so
my point.
basically saying that 7 must be connected to a larger number, right?
Yeah. So like this, if we talk about generally, 7 must be connected to a larger number. And even if in general we will be running out of cases very soon. Now running out of numbers to connect with very soon. That's what I was
Okay,
saying.
well, your claim is correct. Although there is
Is the
like
answer 8?
for 10,
For second, yeah, 10.
it's not 8.
The answer is 12 for the second one.
Okay, I'll tell you what the answer is. The answer is the answer for the second problem is 144.
I think I got the solution.
Oh, okay, wait. Also, it's 8 now, so I think we can probably discuss all the problems. So,
Yeah,
you got
by the way, was my claim correct that 7 can be connected with 14 only?
yes, it is correct. You got 144 as the answer.
Yes.
Okay, then you're probably correct with this. So, could you explain your argument?
First, the number 1 to 6 have to be connected to number 8 to 14 because 8 cannot be connected to any smaller number. Any number from 8 to 14 can't be connected to any small. Sorry, I'm sorry. 8 to 14 can't be connected to another number in 8 to 14.
Right. Yes.
So every number in 8 to 14 must be connected to a smaller number.
Yes.
So
So
7
basically,
must,
connecting 1 to 7 with
but then we will run out of cases for 8 to 14 because we have only 5 options in 1 to 7 and 7 options in 8 to 14.
wait, we have oh, so you're basically saying these two sets are connected with each other, right? They aren't connected within each other.
Yes.
Yes, the claim is correct, and your proof is also correct. So next one.
So 7 must be connected to 14. And
Yes.
after that, for 6, we have two cases, 12 or 13.
Yes.
So we have two choices for 6. Then for 5, we have 10, 11, and whichever we did not choose for 6.
Yeah.
So we have three choices for 5. And then for 1 to 4, all of the rest available numbers in set 8 to 14 will be correct. So we have 4 factorial.
4 factorial.
Yes, 4 factorial for 1 to 4, 3 for 5, and 2 for 6. So we multiply them and we
Yes.
get 1
Okay,
for
that is the correct solution. Nice, good job. So I'll explain what he did. So what he did was, I'll explain it here. I'll give like 10 seconds if anyone wants to screenshot.
Yeah, I got the solution. It was quite nice.
Okay, as anyone screenshot if they want to try these problems and aren't done with any of them yet. Again, take that as a yes. So for number 10. So you got everyone understood by this is true, right?
Yeah.
Okay, so now 7 can only be connected to 14, which is one case. 6 can be connected to 12, 13, or 14, which is 3 cases. But 7 is already connected to 14, so one of them will be gone. So it can have 2 cases. And similarly, 5 will have a total of 10, 11, 12, 13, 14. Yeah, 5 can also be connected to 5 things, but 2 of them will be gone due to 7 and 6. 5 can be connected to 3 things, and 4 can be connected to 4 things. But then with
Yeah.
3, now notice that with 4 you reach 8, one doubling. So on 3, when you double you reach 6, but 6 is already taken. So actually with 3, like the size of the range will decrease. So 3 from 8 to 14, it can be connected with 7. But 4 of them are already taken. 3 can be connected with 3 things, 2 with 2, and 1 will have one final option. So you're 1 into 2 into 3 into 4 into 3 into 2. This is 144. So anyone uh, does anyone have any doubts in this question?
No.
Okay, cool. So which solution should I tell next? third one or fourth?
Why the choice for 3 is 2? I can
Why?
understand.
Why is what? Why is
Why the choice?
why this choice?
Why the choice for 3 is 2?
The choice for 3 is 3 because you have 8 to 14 and with uh, and you already pick one for 4, 5, 6 and 7. So four of these are 7 numbers and 4 of these are gone. So there are 3 choices and any of them will work for 3. So 3 will have a total of 3 choices. Understood now?
Can you just explain the problem
Yeah.
number 3 because I didn't even get it. What's the problem?
Increase the font.
Yeah.
What do you want me to increase?
Problem number 3.
Oh, you want me to increase?
No. I wanted to explain what the problem number 3 states. I'm not able to understand.
Oh, okay. So basically, you can if like some set of consecutive numbers are in left to right order in this like arrangement, there are like 13 cards arranged in some order. If they are like in consecutive arrangement in this, like not consecutive, but if they are in order in this like ascending order, then you can take all of those cards and pick them up. Like for example, here you have 1, 2, and 3. So you will pick them up. You can also pick up 4 and 5. 6 is not present with any other number, and 7, 8, 9, 10 are present here, and 11, 12, 13. So you can pick these up in 5 moves. You can pick up like any ascending subsequence of cards. Like just pick some cards which are in ascending order from left to right. Now you understood the question.
Okay, got it.
And of course, like you want it to be possible for them to be picked up in 2 passes, but you do not want them to be able to be picked up in 1 pass.
Got it.
So should I discuss 1 and 3 right now, or should I give more time for them? Okay, I'll discuss them. So in this we will prove that either A is a subset of B or B is a subset of B is a subset of A. So for this, without loss of generality, like I know there's an order pair, but like just for proving this, we'll assume that mod A is greater than or equal to mod the number of elements in B. So let this be M and this be N. So if your M is greater than or equal to N, and then let us say that uh, A intersection B has M plus X elements, where X is greater than or equal to 0, and then A intersection B has M plus N minus X elements. Wait, sorry, no, not N minus X elements, because these two sum is equal to these two sum. So now, like, I'll just again leave it as an exercise. Prove that the product of these is wait, I mean, prove that the product of these is less than the product of these. So now what happens is you want the product of these to be equal to the product of these. So for that you will need X is equal to 0. Okay, actually another way to do that is you want if like this is like just like mod A is equal to alpha 1, mod B is equal to beta 1, and mod of A union B be alpha 2 and want the B intersection A B beta 2. So you want alpha 1 plus beta 1 is equal to alpha 2 plus beta 2, and alpha 1 beta 1 is alpha 2 beta 2. So that will actually imply alpha 1 is either equal to alpha 2 or beta. So by this like inequality, you will get alpha 1 is equal to alpha 2 only. And that way also you can conclude x is equal to 0. So x is equal to 0 just means that A union B and A have the same cardinality, which would imply that all elements of B are contained in A, because if they were not contained in A, they would be added to A union B and increase the cardinality. So for this, what you can do, so each element of 1 to 5 is either in neither A nor B, or it is in B only, or it is in both A and B. So there are three possibilities for each element. There are 3 to the power of 5 such pairs and 3 to the power of 5 such pairs as well. Well, 2 times 3 to the power of 5. But pairs of the form A comma A, you will have counted them in both of these. So like, let us say the number of such pairs is this, the number of such pairs is this, then after adding them, you will have this area. So this is counted twice. You need to exclude this, but this is just counting pairs of the same subset. And there are 2 to the power of 5 subsets. So you'll subtract 2 to the power of 5. So this will be your answer. Okay. Is that all right? Okay, I'll take that as a yes, and I'll give like 2 more minutes for this problem, and then I'll this. Okay, so I'll tell the solution for the third problem. Then anyone have any ideas?
We can, I think Soham suggested this before, that we can partition the numbers 1 to 13 in like two partitions sets, and like I think by the well ordering principle, like we can sort them, and so hence the problem is I think reduced to number of ways of partitioning to partitioning the set into two subsets. Am I right in this?
Well, sir, yes, sir. There is like less time now, so let's like quickly explain. So let us say you partition into 1 to k, which is what you pick up in the first go, and then you pick up k plus 13, k plus 1 till 13 in the next row. So what you want is these k are present in some order, and then in like this order. My bad, then with some order, and then the remaining k 13 minus k are also present. So the number of ways you can do this is 13 choose k, but and then obviously their order will already be predetermined. But now another issue that you have is you do not want them to be picked up in one go, which is 1, 2 till 13. So you'll subtract 1, and you're summing this from k is equal to 2, wait, sorry, k is equal to 1 till k is equal to 12, because in 13 it will just become the entire set, and for 1 it will become like again, wait, sorry, and for 0 again it will become all of them in one go. So this will become, this is to the power of 13 minus 2, because you're subtracting. Wait, I should probably add this bracket. So you're to the power of 13 minus 13 choose 13 minus 13 choose 0, which is minus 2. So this will become your answer. Is that all right? That's fine then. Okay.
Yeah.
So since there is less time, I will just try and explain. I won't be able to do any problems on this, but well, yes, I can just like suggest a few problems that you can do after the class. So you have a coordinate axis. You can move either one unit right or one unit up, and you start from 0, 0. Then how many moves does it take for you to reach 1, 2? Wait, sorry, this is 2, yes. How many moves does it take for you to reach 2, It takes you
3
3
moves.
moves.
3 moves.
Yes, because in each case you're increasing the sum of x and y coordinates by 1. So you want it to be 3 eventually. So that will take you 3 moves. So once you reach, so now another question would be, how many paths can you reach to choose one? Anybody have any answers for that? It is okay. I'll just tell it. This is one path. This is another, and this is the third. So you can reach this in 3 possible paths. Now, finally, if you replace 2, 1 with m, n, then now how many?
M plus n.
M plus n? Okay, like yeah, m plus n is the number of moves you will take.
Yeah.
Paths will you have to take to reach there.
You're asking number of paths.
Yes.
So we have to take m rightwards and n upwards, so we can take them in any direction. So what was it? I forgot how to calculate that.
M plus n choose n, or m plus n choose n.
Huh?
It's m plus n choose n, or m plus n choose n.
Yeah, I guess.
Okay, so I'll just explain what he said. So you have m plus n spaces. Each of these spaces is either R indicating a right or U indicating, and you follow these m plus n instructions in order. Then you will. So if you have m rights and n ups, then if you follow these m plus n moves in order, you will reach m comma n. So you want m of these to be right. So there will be m plus n. Choose m ways to do this. Okay. Right. So now using this, try to prove does anyone of you know the proofs for this? Okay, so I will just explain. So count number of paths from 0, 0 to n, n. So you want n rights and n ups. So the total number of paths will be 2n choose n. But in the first n moves, you can, let's say you have k ups. So you can choose those k ups in and choose k ways. But in the next n, you must have n minus k ups because you have a total of n ups. So you multiply it with n choose n minus k. And k is ranging from 0 to n. But both of these will be equal, so we can just replace this with n choose k squared. That will be the total number of paths from 0, 0 to n, n. This will be equal to 2n choose n. And we are done. Now, okay, so I suppose there's like less time, so I will have to end now. I'll just suggest some problems you can do. So one really like this grid stuff. So one thing is so yes, I'd suggest you try to find this by yourself, but that would be very hard to do. So if you get stuck, then you can just Google Catalan numbers and find the proof on Wikipedia or something. And then once you're done with this, then you can try this problem. Okay, so that is it for today. If you guys have any questions, then feel free to ask.
Sorry, that was Catalan's what?
Catalan's number.
It's, where would you suggest practicing some counting problems, some any books or particular contest problems, maybe?
Okay, I didn't really practice counting in particulars, I can't tell you, but like you can see past IIM problems, past AIME problems, past AMC problems. Yeah, that's all right, right?
Yeah, okay, I'll check it out.